Hello, everybody. Welcome to our third presentation today. This is given by Dr. Liz Sikes, who is in the Rutgers Department of Marine and Coastal Studies. And she does research on things like carbon cycling and paleoceanography and the circulation of the southern oceans. But one of the ways to begin to get a handle on that is to collect samples. So today she's going to tell us about her adventures at sea. Please welcome Dr. Sikes.
Thank you. And I want to thank everyone for showing up to the third talk of the day, because you've all been sitting and listening to several other things. So John Higgins started us this morning talking about ice cores that they collect by drilling ice. And Sean spoke to us about data from rock cores, which you also have to drill. I'm talking about a different kind of core because I work in soft sediments, and so and I will show you, we basically go out and we shove pipes into the mud. And so today it's mostly a journey. You're going to take a journey with me on a couple of cruises that we've had recently, getting wet and muddy to get the samples that we do the science on. So most of the samples, most of the pictures you're going to see in this presentation come from our Cockatoos cruise back in 2018. And one of the things we like to do to get the motivation up on the cruise is to give our cruises nicknames. And they're always tortured because you want a really good logo and something you can say. And so Cockatoos stands for Coring to Reconstruct Ocean Circulation and Carbon Cycling Across Two Seas. And Puffins stands for, and I don't have the S here for some reason, Puffins stands for Paleofluxes of Unsaturated Alkanones, unsaturated fluxes in the Northwest Atlantic. But mostly I wanted it to be a puffin because who doesn't want to go out and see a puffin? So those are the names, and I encourage you, and I'll put this back up at the end of the talk, to go and look at our website from the cruise. We had a really awesome outreach group led by, and I'm going to make you stand up, Lauren, by Lauren Adamo, who is no, come on, this is the woman who organized the day. And we have lots of videos and explanations on that site that you can really enjoy. And I'm not showing the videos here from that cruise because you can go and enjoy them yourself on our YouTube channel. So please go have a look at that when you get a chance. And so, spacebar? There we go. Why go to sea? We've been learning about paleoclimate all day. But why go to sea besides the fact that it's kind of an adventure and you get really great sunsets? This is actually a sunset in Ile Amsterdam, which is probably one of the most remote islands in the Southern Ocean. And we had good weather, which is why we were all out enjoying that day. So why go to sea? Because we need the material on which to get the samples for which we can work up and actually get paleoclimate records. And so why do we need mud? Well, John talked to you about ice cores. Sean talked to you about rock cores. But layers of mud preserve climate, just like layers of ice and changes in the rocks. So we need a record of climate that is preserved that we can reconstruct and make inferences about past climate. So the sediment record, what's in your mud? So primarily, if we're talking about climate change, I'm looking for things in the mud that preserve a record of sea surface. So mostly what I'm going to be talking about today is our sea surface temperature records. But the way we get a record of climate from the mud is you have your little plankton, phytoplankton, or in this case, they're actually zooplankton, so they eat the phytoplankton that grow in the surface, and they record they're just single-celled organisms, so they actually their chemistry reflects the water that they're living in, and when they die and sink, they end up in the sediments, and through time you build up a record, just like you've been seeing in the last two talks, and then we can go in and get the prize and recreate past circulation from those samples. Maybe I can do this out here. Okay, so planktic surface conditions are preserved in the sediments. So when we're looking for sea surface temperature, we're seeing what, Okay, that just played twice. Okay, so what we're looking for are climate records. And I particularly chose this record of the last 1,000 years or so of temperature, global temperature. This is a global climate temperature record, and it is a composite of local records. So if you look at this, I like this slide particularly because the red part of the line is records, temperature records, global temperature records from measurements. So this is after thermometers were invented and we could actually measure the temperature. So that's pretty reliable. And then as you go back in time, you see there's a light blue envelope around this dark blue record, and that's the variation in the record. So we have an average record that's been compiled from many, many places, and so we can put error bars. So the temperature has been pretty much the same for the last 1,000 years before, if I interpret this for you, before the Industrial Revolution at about 1850. You can smooth that with the green record, but the blue record is basically a composite. So you take all of these things that disagree slightly because they come from different places, and then you get a global average. And so if we look at this same record, but with all of the things that went into it, you can see that there's a number of different records here, and they vary a bit, and they have different periods and stuff. I don't want to talk about that. I just want you to think about the fact that the black line that sums these all up is a compilation of all these records. So I just show you some of these. So John was talking about ice cores and stuff. So we have tree rings, we have many other things, but one of the most important records we have are ocean sediments. In fact, it was from ocean sediments that we first discovered through the paleo records, stable isotopes, and so on, that there were more than 4 glacial cycles. You know, before about 1960, basically we thought there were probably 4 glacial cycles, but now we know that there are many, many more. So we need records, actual records that we can compile, and we need a temperature proxy, because if I go back one, yeah. So before here, this is the one I wanted. So before thermometers, all of these temperature records are based on proxies. You've got to have some sort of stable isotope. You've got to have something that preserves a record in a stable way that we can go back and look at it and analyze it and get information from it. So one of the proxies we use are these little forams, these little microfossils. These are just a couple of different species, and we can either do assemblages on them or actually get their stable isotopes or their trace metals, and we can actually get, at this point, we've developed these proxies well enough, we can get quantitative records of temperature, which is important. So just knowing whether it was warmer or colder is very interesting, but how much warmer and how much colder is really the whole point. This is what we need. So, and the other thing is the sediment cores can give us long time climate records. So John had to, whoops, I'm hearing an echo. It's okay, give yourself. So John had to go to extraordinary lengths in his ice coring to find ice that was old enough or older than the depth to the basement. Whereas with sediment cores, we can just keep going down through time. Now I core, not drill, so we're limited to how much length of pipe we can punch into the earth, but you can get these tens to millions of years. And so the thing that I do in my science, there's 2 things I do, and I'm only really going to talk about sea surface temperature today, but I look at, so this gold record is the change in CO2 since the last ice age. So it was lower at 22,000 years ago than it was at 8,000 years ago. And these are just 2 composite records of temperature for the globe. The red one is the southern hemisphere, and the blue one is the northern hemisphere. And just in those 2, those are composite records, but the northern hemisphere and the southern hemisphere warmed out of the last ice age in concert with that change in CO2, but they were very different. That's why all these different records are so important. So we need to go and get records from all over the globe to combine them into a global temperature record, and sometimes we need to take them apart and look at how the planet responded in different places with different cadences. So where do we go to find climate records? where we don't have information and we need more information about climate. So I pretty much work in the Southern Ocean because there aren't a lot of records there, but I also work in the North Atlantic. So where do we go to find mud is where we can find it. And that's the hard part. There's not always the right mud. There's not the mud with the right fossils. There's not the mud with the high resolution. So finding the mud is the trick, is one of the tricks. So cockatoos, which we went out in 2018, we left from Perth, Western Australia, and we went almost halfway to Madagascar. And if you look at this, and I'll have my next slide shows this better, but we were looking for the right mud. And so one of the things about the deep ocean is I primarily work with fossils. Carbonates dissolve if the water is too deep, and if you want that lesson in chemistry, ask afterwards. So that ship's track looks a little bit drunken because if you find the mud, then you got to go back and get it. So here's just a picture of the cores. This shows the topography, if you will. So the more red colors are shallower. So you notice that all of our cores are coming from places that aren't blue because there's no mud where it was blue. So it would be really nice if we could just go out and say, if you're a tree ring person, you go out, I want a pine tree right here. This is where I want to know what the temperature was in the past. But it's a desert, so you're not going to find it, right? So you have to work with what you've got. So back for the cockatoos, we spent 48 days looking for mud. We found a lot of it. The other thing is you need to choose your ship. Now there is ocean drilling program which goes out and drills very long cores that gets us back millions of years like Sean was talking about. But if you just want, what I'm interested in is the last deglaciation, so the last, say, 20 to 40,000 years. You know, you've got to have the right ship. And this is just a picture of the core lying along the side on the Atlantis. It's got to be a big ship. You can't do this kind of stuff from a dinghy. So how do you choose your ship? It has to be big enough to do the job. And in the US, that means we go to UNOLS, which is the University National Oceanographic Laboratory System. It's a authority that basically lends us the ships to do the work, and the kind of ships we need are global class. They're the big guys. We got to have the big ship. So this is just a picture of the Thomas Thompson on which we conducted cockatoos, sitting in Perth, waiting to go out. So we took her out of Perth in 2018. We've also cored on the Roger Revell. This is the Roger Revell in Wellington, New Zealand, waiting to go out for the cruise we had in 2005. And just to show you, yes, we were successful. All of those red cores are cores from that cruise. And I will show you some data from that cruise at the end of the talk. So you got to have the right ship, you've got to have the right mud. And our most recent cruise was on the RV Atlantis, stands for Research Vessel, out of Woods Hole, Mass. And that's the cruise for which all of our outreach was done. And there's two activities next door based partially on the stuff we did there. And so puffins, we were working off New Jersey and the Scotia Shelf. And this brings me to how do you find the mud? So this is also kind of a wild cruise track. But if you look at that, there's two places on that figure where there's some colored data. And this is pre-existing bathymetry. So if you're lucky enough to work off of the US and Canada, both countries have mapped the bottom, the seafloor bottom for the bathymetry, because, and actually this is an interesting aside if I may, back, I think it was in the 1980s, but some don't quote me on the time, but about 30 years ago, there was a law of the sea that said you can have an exclusive economic zone and you can go out to the shelf break, which is where you have this. So this is all the shelf breaks. So we have a flat undersea area and then it drops very quickly. And your exclusive economic zone could encompass that, but you had to prove you had a shelf. So they mapped all of this. So we took advantage of this for the Puffins cruise, and those are just the ship's track and our cores. A lot of the zigging and zagging is to see if there was mud there, but you can see the triangles tell you where there was mud, because there wasn't mud in a lot of the places we were looking. So I just want to zoom in off the Scotia Shelf, off of Nova Scotia. And so what we were working from, we had really good information. And so we came in. those two diamonds in the white part, we bounced our cores. Got nothing. So, but we came down, I can do it for the people online with the mouse. So we came down here, and what you can usually guess if you've got these canyons is that the mud, the sediment in between is undisturbed. And that's what we're looking for. It has to be sedimenting like I showed you in that figure for us to get a record through time. And so we came down, and you can see we steamed down. Oh, that looked good, so we went back and popped a core there and did another triangle, popped a core there, and then it all looked good. So we were pretty lucky. So if you have pre-existing bathymetry, you can get a pretty good idea of whether there's going to be the right topography to have the mud. When we don't have that, we have to do bathymetry on the fly. This is just a screenshot from during the cruise, the bathymetry that we were steaming over. And so you can see, we can see bumps and lumps, means it's probably not very good for coring. But that's not enough. You also have to look into the sediment. And so we also need what we call a sub-bottom profiler. So this is just a single track rather than a multi-beam, and you can see that there's a black line. That's the hard surface, that's the bottom, and then we can't see anything underneath it. I'm not going to give you a tutorial in reading 3.5 sub-bottom penetrating, but that's no good. And it's lumpy and it's bumpy and you can't see anything. What we're usually looking for is something that has a sub-bottom reflector so we can see into it. We can see that the mud's soft, and we can see some sort of reflector underneath there that tells us we've got parallel or sedimentation. What's wrong with this one is that crossover there. So what we're looking at is that's a slump at the bottom of a slope. So a big chunk of mud came off and went plop. It's very soft, but it's very disturbed. So what we're really looking for is something more like this. Okay, it's a little gray. We've got some multiple sub-bottom reflectors. So maybe that's going to be a good place to core. So we spend a lot of time standing around in the computer room looking at all these sets of data and trying to figure out if the mud's any good, because the equipment I'm going to show you next is very heavy, and it can break and people can get hurt. And so you really don't want to send your rig over, and if it's rock, right, it'll bounce, it'll bend, it'll break, and sometimes it literally just falls off the end of the line. It actually breaks the wire. So you've got to do a lot of thinking before you put your rig over the side. So once we find the mud, we have to sample it. So this is just an online, you can get this online, but basically, how do we core? We're basically jamming, so that's a 5-ton weight on the top, and basically a big heavy pipe, and we jam it into the bottom. There's two different ways we can core. We can gravity core, which simply the core just goes in and it jams into the mud. But we can also piston core. So these piston cores have a plug at the bottom, and so as it's going into the mud, it sucks back, so we can fill a longer barrel. So I don't want to go into the fine details of piston coring, but there are two different ways to core. But the cool thing about the piston core is we can get 10 to 12 meters if we've got the right kind of mud. A gravity core, you kind of max out at about 5 or 6 meters, so like 30 to 40 feet. So it's a lot less efficient, because you're just squishing all that mud into a pipe. You're not pulling on it as well. So when I say pipe, I mean pipe. Okay, so we get that pipe, and these lengths of pipe are too long to have all on the deck at once. So you see we've got this whole stack of pipes, and we have to rig it on the outside of the ship. So here's just one pipe, and then that's the seam to hold the two pipes together, and they're rigging, these guys are rigging it, and sometimes you have to lever it with a 2x4, I kid you not, really high tech, really high tech. So what I'm going to show you is, so we rig that, and then we hang it over the side. And so that's the weight in the bucket, as we call it. And so that's going to go over. And what they're doing is they're actually rigging the trigger. So if we piston core, we have a trigger that helps it free fall the last little bit and pull that piston back. And if anyone wants a tutorial, I'm happy to give it to you. But so that's the core in the bomb ready to go over. And so here they are rigging the trigger, and you can see everyone's wearing hard hats. The guys who are really doing the work are also wearing gloves, and everyone's got to have steel-toe boots, because there is nothing on that rig that weighs less than about 30 to 50 pounds. including some of the nuts. Okay, so it's going over the side, and I just want to show you this. So it's in that bucket. It has to get lifted out of that bucket, and then we have to send it down. And you can see this is my favorite coring tech, Dale Hubbard, saying, go down, stop, okay? So it's going out, and then I just want to show you a picture of the rig. That's what it looks like going down. And then there's this 2 or 3 hour period where this is all you see. The wire, it's over the side, it's going down on the wire, it's going, hopefully hitting properly and coming back with mud. What I do have is a video, which I should be able to play here. There it is. This is bringing the core in. So now the core is already back in the bucket, but now we're going to bring it on side. It's time lapse, so it's going to go a lot faster than it looks. But what it is they're going to secure that in the bucket, make sure it can't get away. Then they're going to put a lasso around the barrel of the core, and you'll see this second crane comes in, and it's going to winch with it's got a sling, and it's going to winch that thing up, and then we're going to put it on the side of the thing, and we're securing it and all of that. Okay, we got it back. Does anyone need to see that again? Okay, good. Sometimes I think these things go a little bit fast. Okay, so now we've got it up on the side. So I showed you we have these big, heavy steel barrels. Well, we filled it or slid inside of it a plastic core liner. Back in the olden days, like before I was born too, they would just get a plunger and shove the mud back out of the barrel into a tray. Yeah, so now you're shoving it into the thing and you're shoving out, it gets a little disturbed. So now we have a core liner, and I'm going to show you the next steps to getting our core out of the barrel and into a place that we can work with it. So you have to take this is the core cutter. It's a really heavy piece of metal with a bit of a blade on it. Then we have to shove it out. So you can see it's starting to come out. So you can see a white core liner there, and we're pulling that out of the core. So once you get that to a certain point, you want to put a cap on it so the mud can't come out. This is just another photo of a different core, and everyone's literally pulling that thing out. And you got to pull so to get it out. And then it comes on board. So to keep costs reasonable, we use things that we can find. So that's actually PVC sewage pipe. And so it comes in 10-foot lengths. So we have 10-foot lengths that we bring on, and then we have to, and you can see it takes everyone to hold that. So it weighs a lot of weight. So we're going to cut it into smaller sections. So we bring it on board. And before I show you that part, I want to go back and talk about the mud. So it's important to look at that. So this is actually our core catcher. So there's the core cutter, and inside it, it's just and this one's actually the reason I took a picture of it, it's all mangled to all bejesus, I think is polite enough. But it's just basically a piece of metal that's been cut into fingers and wrapped so that the core goes into the barrel, and then it gets stuck and it can't come back out. So, and that's really important because many of these cores are coming up 2,000 or 3,000 meters worth of water. You can wash your core right out of the barrel if you're not careful. So it's quite an art. So here's the core catcher. You take that off, and now you can see the mud. So what I'm doing here is, this is the bottom of the core, and it looks kind of gray-white, and the mud on the outside looks kind of creamy, right? And so one of the things you want to do is like, okay, do we have mud? Does it look good? And so you're actually, because the other thing is, once we cut this up, it's going to be 2 days before we see what we got. 2 days. So this is all we get for 2 days. We get to wipe the outside of the barrel with our fingers, maybe roll it around in our hands. Sometimes it overpenetrates and you get a couple of bags of mud, but yeah, we get muddy at all stages of the way. So yeah, but for 2 days, this is all we get, but now the work begins. So we've got to cut that 10-foot barrel into 1.5 meter sections. So on the right, this is a core pipe cutter, and I'll show you a video of that next. And then that's that's a cheese slice and a spatula. So what we're going to do is cut a 1.5 meter section and cap it. You can see Xana here. That red thing is a core cap. She's got a electrical tape. Sometimes the mud's really stiff, and so you don't have to move very quickly. Sometimes the mud's really sloppy, and you got to get that cap on before it all goes out of the barrel. So, getting muddy. So we're cutting it, and then there's Natalie with her tools ready to go, and there's a 1.5 meter section ready to go in. So we start from the bottom, because you start cutting from the bottom because you know there's mud there. Sometimes, especially with gravity cores, it's not so sure where the top of the core is. If you didn't fill the barrel, you don't want to just keep cutting because the water and the mud's just going to go. So here's Ryan and Cassie trying to figure out where the top of the barrel, where the top of the core is. So they're having a look at an angle, right? You don't want anything to pour out until you're sure. Here's another attempt. So we couldn't find the top of the mud, and we said, okay, well, let's just drill a hole there. No, water came out, so we know there's no mud there because the water's clear, right? So it's all these getting wet, getting muddy, trying to make sure you're treating the core as best as possible. Here's a particularly funny example. So one of the things you do is you siphon the water off the top of the core. And so this is a barrel we really couldn't figure out where the top of the mud was. And when I say siphon, has everyone done a mouth, like suck on the water and let it go? Yeah, I'm sparing you those photos. But there's a lot of that goes on. So eventually with this one, we just decided, all right, we're not sure, so we're just going to cut it. And this is another video. And pay attention to they're using the pipe cutter there, and I want you to have a look, because it's actually very physical, because you turn it's got a blade and it goes around, and you turn a half crank and you go around, and turn a half crank and you go around. So it's actually quite, it's not hard, but it's physically intense. So here we go. And the ship's moving around too. Oh, okay, we made a good guess. There wasn't any mud above that because the water's coming out clear. So yes, getting wet and muddy is part of the game. And so if all is good, you have a really well-behaved core, you can just work on it on these standing out there, but it doesn't mean you're not going to be muddy, but you can work it up in a more, not civilized, nothing of this is actually terribly civilized, but it's but a more stable environment. You're not standing the core up and looking down, and that's how we like it. So yeah, this is just a picture at the end of a session where everyone's pretty happy. And that mud also makes pretty good war paint as well. So, so now that we've cut the core liner, we scan the whole core. So what takes 1.5 days to 2 days after we pull it up, cut it? All we get is a view of the ends if they're stiff. We have to run it through a multi-core scanner, because when the core is still round, we can interrogate it with electronic beams and magnetic and stuff like that, and examine it. And if we cut it up before we do that, we can't go back. So it spends a day in this van. First it has to warm up, and then it has to run through this scanner. I'm not going to bore you with a video of that. It's very boring. It just goes zzz, zzz, zzz for 12 hours. So we scan the core, and now that we have to do that, how do we get to the mud? We need to split it. So the first thing we do is the core is in there, but we're basically, you cut down the core liner on both sides. So you cut the plastic, but you don't want to, we've taken a core, right? It's undisturbed. We didn't drill it, we didn't stir it up. It's this beautiful core, which just the very outside edges might have gotten slid on. So we cut the two sides of the barrel and then plop it open. So we cut the two sides, and so we have both sides open, and they've taken a X-Acto knife and cut the end of it, and then we're putting two plates in it, and then we're going to plop it open. There's a really good video of this on the Puffins site. I encourage you to watch that. Way better than the stills I have here. And so then we have the two halves of the core like that, and now we can take it into the lab and begin to work it up. This reminds me to say, safety first. Those are very loud steel core, skill saws that we use. Oh, and I didn't point out, but you notice it was also we worry about microplastics. And so that Sujata was cutting the core. Someone's following her with a vacuum cleaner, right? We try and collect all of that. And if I go back, I can go back a couple. You can see, I should point that out. See all that plastic? That is keeping it from going down the drains and off the ship, and so that we can vacuum that too and make sure we don't put any more microplastics into the ocean than we already have to worry about. And so yeah, there's a lot of covering that we have to try and keep that from happening. So now that we can see the mud, the fun starts. Or should I say the science? Okay, compare and contrast. So yes, even in these cores, this is a core, one of the cores from Amsterdam, and you can see these color changes. They're very indicative of climate change, even without doing any of the actual measurements that we're going to do. The tops of the cores in the Indian Ocean tend to be brown. That's to the right on this picture. And then as we go down into the last ice age, they're green. And that's probably fronts shifting and changing from forams to diatoms, but definitely climate related. And this is a core from our Puffins cruise. It can be very, very brown because we're near shore. We're getting a lot of terrigenous sediment, as we say, dirt coming off the land. And we think that these flecks, when we open that core, that's the other thing, is being there and collecting your own samples is really important. We open those cores, and I had a look at them, and I'm like, that smells like charcoal. You could smell the charcoal. Now, 2 days later, you couldn't smell the charcoal, but when the core had just been opened, that's really important. Sometimes we open them up and you smell swamp. You smell, sulfur, so you know it's anoxic. So these things that you note in your descriptions are really important. And that's the next step. We have to describe the core. So off the Scotia shelf, it's not showing up so well here, but we actually had some really marvelous red layers in the core. And those are really indicative of, the fact that you have a color change tells you that either that something was different in the past. Our guess for here was during the last ice age, we had all of those red beds that you saw in the noon talk, the midday talk, same sediments up off of Nova Scotia, probably running into this core during the ice age because the glaciers were just grinding it off. Anyway, the other thing you can see in these two slides, and here's just a little bit, can you see it better in that one, the big red section? Yeah, you can see it better in that one. So one of the things you notice in both of these pictures is we have these little pegs on the side of the core. Now it costs $70,000 to $100,000 a day for that ship. So by the time we bring that mud back, we've spent $1 million in ship time. We have somewhere between, in this case, we had 6 cores, and in the Crocatoos, we had 36 cores, but those cores are worth a lot of money, and so it's our job to archive them and make sure that they're usable for everyone else. And so one of the things we do is we peg them. So you measure them very carefully. You put the pegs in, because one of the things that mud does that rock doesn't do and ice doesn't do is it will dewater and shrink. There's nothing you can do about that. As soon as you bring that core up and it's no longer underwater, it's going to dry out. We put it in D-tubes, we cover it with plastic, you'll see all of that, but it will change. And so one of the things we do is we mark how it was when we got it, and then if it shrinks or whatever, then we still know when we describe it, we still can preserve that stratigraphy for later. So we measure it very precisely, and we put these pegs in. And here's just a picture from Crocatoos, same thing, just different mud, but yes, very carefully, you can see the little yellow square is still there. And once we've got it pegged and we described it, one of the things we do is we take a picture, okay? Because you can describe it and you can, peg it and all of that, but like I said, the way it comes up is very different from the way it's going to be in 6 months. Just that picture I showed you where the core went from brown to green, we went back and resampled that core 7 months later, and all of that green had turned to yellow because it's chlorophyll and it just faded. So it's really important to do your job so that these cores are worth the amount of money and time. So here's just another picture of Ryan. And so, yeah, this was the cruise in 2022. We were still under COVID protocols, and so we were wearing masks. But this kind of gives you the whole thing in one picture. So Ryan is pegging this one. This one's been pegged and it's wrapped because it's not, we have one half is archive. We don't touch it unless we have to. One half is working, and we can work on that first. And when that's all gone, then we go to this one. And this one's already been sampled. So when you take mud out of a core, out of a sediment core, you replace it with we usually use a foam. It's not styrofoam anymore, but one of the foams, because the core, if it's new like this one, it might slump in, but you also need to leave a record where you took stuff out. So you're basically, everything you do has to be accounted for so that the next person who comes along can still use the core. And you can see here, they each had their little checklist. This core has that, and that done, but we haven't done that yet. Okay, so we have a whole protocol to make sure that we've got it ready. What we've done to it is recorded, and we can recreate it later. Because what we've already done with some of these is we've gone back and resampled them. So we ran up a few things. We got a little bit of preliminary data, and we said we need to go back and get more. So, yep, there's a whole protocol. Just another picture of Ryan. He's sampling for calcium carbonate there. These guys are trying to figure out where to put in that clear plastic tube that Xana's holding on to is called a U-channel, and we're going to take a whole long slice out of that core so that we can run XRF on it. You heard about XRF from Sean earlier, so we're going to do X-ray on that. But so we're just figuring out so she's trying to figure out which side of the core and how to do that. And then when you're done, you wrap it up. If you're done sampling, but we also. But let me show you how I sample a core. So what we do is, we don't know what we've got yet, right? We've got a core, we can make some guesses based on the multi-track that we just did and the colors. But so we routinely sample, you just sample at a given interval down a core and then have a look. And so we've got these little scoops. It doesn't really matter, but we're taking pieces out of the core and we're putting it in the bag, and we're going to go home and start the actual science. And so, you're measuring very carefully again, you're putting it into the bags, and sometimes when you're done, you just have to smile, because it's like 48 days at sea. You go a little crazy. One other thing we do is, because taking a mud core, a piston core and a gravity core, it's pretty violent. You're dropping a very, the weight on top of that weight stack starts at 5,000, pounds. So it's like, bam, right? So sometimes, and frequently, actually I do this routinely, we also take a gentle core where we can get the core top, because one of the things that helps you know if there's a change in the past is if you know what today looks like. So this thing is called a multi-core, and you can see there's multiple barrels inside of a frame, and there's actually, it's hard to see, but there's a weight stack inside that net. And so it goes down, and it very gently, it goes down to the bottom, and then it very gently takes a core, and so you preserve a core top. And so I just wanted to show you one other way. So these cores come out, and you actually have to push pop them. So what they're doing here, I've got a video. It's out of focus because it's a video. But you basically take that plastic barrel full of mud, stick it on the stand, and then you basically shove the mud up by pulling the barrel down, and we're slicing it. So what they're doing is they've got, so if you can see in the woman who's standing, that's Hillary, she's got a ring in her hand, and that's 1 centimeter. So we're going to push the core up 1 centimeter, put that ring on top, push it up till it fills that ring, and slice it off and put it in baggies. And so, and it's a very slow, it's a very laborious process. And so here we go. I'll just stop it there. So baggie, slice bag. But what it takes so long is like, yeah, everyone comes in and has an opinion, right? Let's take some pictures. But you can see as they're doing it, that's the bottom of the core, and it's getting higher and higher and higher until you're done. So there we go. So yeah, we do a lot of stuff on the ship. We archive that. Of course, you have to record it. And here's just a picture of Aiden working on that. And you can see, this is, the reason for this picture is he's pretty muddy. So when we're done with that, when we're done with the multi-core, we have baggies of mud. When we're done with the long cores, we have halves of cores in what we call these D tubes. And so this is where we start. We start at the bottom, we rack them up in the lab. and then we have to ship them home. So this next picture is the cooler van that's taking these cores home. So we put them in a very secure rack, put them inside a cooler van, ship them off to the core repository. And so Sean showed you a lot of pictures of continental cores. These have to be kept refrigerated. They're kept at 4 degrees C, so just above freezing, in a cooler van. And so we try to keep them moist and cool. 4 degrees is about what the bottom of the ocean is, so that's one of the reasons for that. So, okay. So as I've showed you a few humorous pictures, one of the things we like to do on the ship is we like to squish styrofoam cups, because when you put a styrofoam cup over the side or down under the amount of pressure, to give you an idea of what kind of pressure there is at the bottom of the ocean, they shrink a lot. So this is part of the team sitting there with the cups. You draw on them, you put them in a laundry bag, and they come up a lot smaller. So that was one of the fun things we do. And actually, this is one of the things we like to do. We've done numerous times with classrooms. So we've had classrooms of students put their names and stuff on a styrofoam cup, and then we give them back to them. And I meant to bring one with me today, and I forgot, but they're about this big when they come back. So it's a lot of fun. Something to do while you're out there. So there is a lot in that mud. So what we're out there for, doing all this slicing and heavy lifting, is looking for these guys, as I said. So I showed you a picture of our forams, but let me show you a picture of them in real life. There it is. There it is. Yeah, they're microfossils. They're tiny. We use a microscope to sort them by species. But sometimes you get cool things in the mud that are a little bit bigger. On that Nova Scotia cruise, the core that we took up on the shelf had these gastropods and these trumpet shells in them, so that's cool. You never know what you're going to find, and that's part of what I enjoy about doing this. So you know, why else do we go to sea? I mean, I can say the other thing is, like I said, you know, it's really important to be out there when the mud is collected so that you can see what it looked like at the time and you can understand the environment that it's in. And so, but it's not always that nice. You know, why do we go to sea? There is, you know, because I have had numerous cruises where the weather looks a lot like this, and I will spend a lot of time in my bunk when it looks like that. This is actually from one of the cruises. Standard operating procedure is if the waves get too high and the weather is too rough, you steam into the sea, because you're fine steaming into the sea, but if you're going a beam, you can tip over. So this was one of the days where we had to steam into the sea. But that's not all of it. One of the best parts is dolphins love ships, and they come and they will surf off the bow. These guys surfed. This is off of New Zealand. We saw daily off of Nova Scotia, we had dolphins. We had fleets of dolphins. What are they? Pods of dolphins coming to the ship and surfing off the bow for hours at a time. And yes, that's fun to watch. You can just stand there and watch that forever. Another thing that I enjoy about going to sea is the seabirds. I'm a bit of a avid but amateur bird watcher. These are Eel Amsterdam albatross, one of the rarest in the world, only because there's a small island that they nest on, so there's only 500 of them. This is another. These are giant petrels. This is Eel Amsterdam in the background. What these guys are doing is they're doing the same thing that the dolphins are doing off the bow. They were cruising on our airwave, and so they were hanging there for 2-3 minutes or so, and then they would peel off and go back up and slide back in to the wave. And so they surfed with us for several hours. Not all the same ones, but we had a lot of, we were steaming and they were enjoying the ride. And when it's calm and lovely, sometimes you get a whole flotilla of them. But in the end, we go to sea for the data. So this is a core we've just sampled. And in a year or two, we'll get something like this. So this is sea surface temperature records from off of New Zealand. That was the cruise we took in 2005. And so what we're looking at here is just the change in temperature across. So this is the last ice age. It's colder. Up is warmer. And one of the things this paper was showing was not just that it got from like I said, it's really important to be quantitative. It's not just that it was colder back then, but how much colder was it? And what was the pattern of the deglaciation? That's actually something, when I showed you that picture of the CO2, there's 2 steps in the deglaciation. So which came first and which came later? And I'm very happy to talk to anyone if you have questions about the temperatures and the carbon dioxide. And with that, so yeah, but that took 3 years to generate. I want to just put another shout out for our official page, and thank you for your attention. Questions? In the back, yeah.
How deep is human contamination of the first layers of mud that you see?
That depends on the sedimentation rate. So, so in these cores, most of these cores that I work on, we get a centimeter, 1 to 10 centimeters, 1,000 years. So if we're getting 10 centimeters, 1,000 years, 1 centimeter would be anthropogenic. We would expect anthropogenic influence. The higher the sedimentation rate, the deeper that layer will be. So about, a couple centimeters. So once we're out of, So what I usually talk about is the Holocene, especially because these gravity and piston cores, you blow the top off, so you're not really sure where 0 is. Yeah. Good question, though. Thank you. I saw another hand. Yeah, over here.
So you're taking samples from the bottom of the ocean. How do you turn it into sea surface temperature? And how do you measure surface temperature?
That goes back to, if I can get it out of escape. Okay, can I get this to, I can go back to this, but basically what it is without being able to find the picture, it's the bottom of the ocean, but the things that we're looking at in the bottom of the ocean are those forams, and they grew in the surface water. So when they fall down and end up in the mud, they're still telling me what the surface was, even though they're not at the surface anymore, because I'm looking at their dead bodies. So by the time they get down there, they're already preserved what was in the surface. Is that?
Yeah, that makes sense.
Okay.
How do you get temperature out of that?
Well, from the forams, I can do an assemblage the same way you can look at an assemblage. If you look at a bunch of pollen, that's something that's more common. But if you've got a lot of palm trees and not a lot of fir trees, it's going to be warm, right? So we can look at the assemblages, so how much of which foram. But what we usually do is we run the stable isotopes. So the Delo-18 in the calcite in the foram records temperature, and how much. So they also have these little inclusions. We can also get temperature by looking at how much of a it's not a contaminant, but how much of a trace metal. So it's calcium carbonate. You can substitute calcium with other. One does not substitute. What happens is thermodynamically, if I may, these other cations substitute into that matrix, and the warmer it is, the more you get, and so we can actually get a quantitative temperature from that with these trace metal inclusions, if you will. So that's one thing. And the other thing I use is, and I haven't talked about this here, the phytoplankton actually osmoregulate by changing the number of double bonds on some of their compounds, and we can use that as well. So it's all chemistry. We basically take that and we put it through a machine, and we've calibrated the response to temperature, and we get it that way. Yeah, it's the same way that you do it in ice cores, actually. Yeah.
Do you use the cores for anything but temperature?
Yes. I do routinely run stable and carbon isotopes on them, and with the stable isotopes of carbon, I can tell you how much CO2 was in the water. I can give you an estimate of CO2. So when I talk about CO2 changes, so I'm also looking at those same forms. It's the same machine, same measurement. I can also get carbon isotopes, and then I can tell you CO2 levels, which is the other thing I'm really interested in. So I'll leave it at that. There's lots more you can get as well. Yeah, back there.
So with that carbon, how about how that relates to what was in the atmosphere at that time? How do we determine that?
Correct. So the atmospheric CO2 changed. So we have to calibrate it to the atmospheric CO2 and the C13 in there. And so one of the things we can do is look at how much CO2 is in the deep ocean. And I haven't talked about this. I can also look at benthic forams, so bottom dwellers, and their isotopes tell me how much CO2 is in the deep ocean relative to the atmosphere. So there was a question, if you were here for John's talk this morning, the first talk of the day, someone asked, well, you know, where does all that CO2 go in the last ice age? It went into the deep ocean. And I'm the person, he measures what was in the atmosphere. I measure what was in the ocean, which is why we should have had my talk after his talk. But anyway, yeah. So yeah, it's all very interesting stuff.
So how do you know how old a given slice of the sample is?
There's a couple of different ways to do that. One of the things we do routinely is we radiocarbon date it. I work in the realm, if you work in the last 30,000 years, is where I stick, radiocarbon is the go-to. But there's other ways to do it. If you caught Sean's talk, we use everything available to turn depth in core to time. And that is actually an art, and that is probably one of the most important things we do besides the actual science, is to get the time right. So it's not easy, and we're very careful, and we work really hard at that without giving you all the other ways we can do it. We can wiggle match and stuff like that. So, but it's a good question, because that is the $64,000 question, is like, where are you in time? It doesn't matter what the temperature is if you don't know when it was, right? The temperature is actually the easy part.
Does your analysis tell us anything about pH changes over time?
Not my analyses, but that was the one I was running away from. So yes, we can measure pH. You can measure boron isotopes in these forams as well, and there's a relationship of the boron. It changes its, lots of chemistry now, but it changes its speciation in the ocean based on the pH. And that boron is also gets included, if I may. It's an inclusion. It's another one of these metals, trace metals, that goes into calcium carbonate. And we can measure the boron to calcium ratio, and we can measure the boron isotope. So that's, I think it's B11 to B10 are the two isotopes, if anyone really wants to look it up. Del B11. So yeah, we can measure pH. That's a new one, actually. That's a really great question, because that's one of the things that's probably only about 5 years old. And it's exciting.
Conclusions from that part of it.
Oh, we can go back. That's why we were so careful with our cores. So one of the people who's doing this actively is a woman, a scientist at Lamont, Bärbel Harnisch. And so she's actually gone back these cores, right? One of her students worked on one of my cores, right? So we use them for the stuff I'm interested in, but we're very careful and we save everything. So now we can go back to the cores that were taken 30 years ago and do that measurement. That's why we're so careful. So yeah, good question.
I may have missed it, but I'm not sure how deep you're going.
These cores, with my cores and with the sedimentation rate, it's a dance, right? How fast is it sedimenting? How hard can I hit it? Maximum maybe 150, 250,000 years. With the drilling programs, you can go back a lot further. It depends on sedimentation rate.
But the depth of the
pipe?
cores.
Yeah. Well, I'm going to say it's a dance. How hard is the mud? How heavy is your weight? And you have to make an assessment sort of on the fly from looking at that sub-bottom penetration that I was telling you. So, and then that's when I have a conversation with my chief coring technician, Dale, who is, like I said, one of my favorite people in the world. And we go, does this look like a 3-piper or a 4-piper, or is it going to be a 2-piper? So it's really a guess. So it's always on the fly, right? Because it's like, how hard is the mud? Do you think you can put another pipe on? Sometimes we put one in, it over penetrates, right? It was too soft. All right, let's put another pipe on it and go back. So.
And is it just one shot that you do it?
You can re-core in the same location. I don't usually, because I have different objectives. But yeah, you could do two. You could do a long one and a short one. We haven't usually. Yeah, it's your choice. So yeah, if you didn't get it right, you can do it again. Like I told you, we bounced a few cores, right? That first slide of the puffins, we bounced a few. There was a place in Cockatoos where we bounced a couple, but we got it right the third time. So yeah, it's just, yeah, it's your choice.
Hi, thank you so much for your talk. I wondered about contamination. It looked to me like, I was thinking those sewage pipes were iron, but it looked like they were PVC or something.
Mm-hmm.
But is there contamination from that or from the material, maybe not saran wrap, that you wrap the cores with?
Well, the answer is yes, depending on what you're looking at. Now, so that PVC liner, so now you can have, that's plastic, so you can have plastic contamination. One of the things we do to avoid that is when you're sampling that core, so we're sampling it, you don't sample any closer than about 1/2 centimeter to the edge, because basically that mud slid into that core, right? And so that outside bit is messy, so you just don't go there. And if you are doing, or if you're doing metals or carbonate, the plastic doesn't matter. It doesn't matter. But if you're doing organics, which I also do, you then, what you do is when you, if you have, and we do always cover it with saran wrap, you just don't take the top, you just slice the top off. So it's really more of a surface contaminant. It's kind of hard for it to penetrate, yeah. Actually, the worst thing we have to deal with is when you cut that core. Like I said, we use that saw, and so that saw is making all those bits of plastic that you saw. And that also, depending on how deep, this is an art, right? It's always an art. So the barrel is, let's say, 1/4 of an inch thick. You don't want your saw blade to go more than 1/4 of an inch plus a millimeter into the barrel, into the core, because otherwise it's pulling all that garbage. I'm trying not to use I go to sea, and so sometimes I talk like a sailor, and I'm trying to avoid that. So you don't want all that stuff in your core. How's that? So yes, we're aware of it. But what contaminates what is what you need to keep in mind.
The oil companies doing offshore drilling share any of their cores with you, or?
On a one-to-one level, no, because anything that I'm interested in, they're not interested in. That's why I have to go and get my own cores. But depending on what you're doing and what your interests are, sometimes maybe. A lot of the stuff they do is very proprietary, and they hold on to it because it's worth money. So I do know that they do share, but not with people who in my field, because I'm looking at the last 30 to 100,000 years, and oil, yeah, you got to go back at least 50 million years for that to be a point. Like, you can get gas hydrates, but no, it's just pretty much, it's like we don't talk to each other, not because we don't like each other, but because we're just doing completely different stuff. But that's a good point, though, yeah.
Do you find any significant fossils in cores, say new species?
No, yeah, so he asked if there's any new species that we find. And the answer is pretty much no, because there's only about 30 species of planktonic forams that are alive, that have been around for the last 100,000 years. And they really haven't changed. And people have looked all over the world. So not in the planktics. Benthics, there are thousands and thousands. And I'm going to say if we found a new one, we wouldn't have noticed, because I am not a forum assemblage specialist, and so I wouldn't know a weirdo when I saw him, if I may call him that. I wouldn't know an unusual one. I'm laser focused on 3 or 4 species that are good for chemical analyses. And if we find anything really weird, we send it off to one of the specialists, but we're usually not looking for them. So yeah, we're probably missing a lot, actually.
How has technology over, say, the past 10, 20, 30 years impacted what you do, and what do you expect going forward with technology to change what you do?
GPS, navigation, we actually know where we are. That's very cool, because it used to be a lot of dead reckoning. And before that, there was, I'm trying to remember. Sextant. Well, we had sextants. We could navigate, but you can tell where you are, but only like twice a day. And so between those 2 times, you were kind of like, yeah, we're in this area. So it was the GPS, so we know exactly where the core is. The other thing is dynamic positioning. So the ships, it used to be, when I first went to sea, you know, when you came on station, oh, you found the mud, okay, stop. Now you have to turn the engine off, or at least you have to turn the propeller. You don't turn the engine off, you never turn the engine off. Turn the propeller off so that you're not cutting the line, because it's very easy to drift over your line. You know, the water's going one way. Even in the middle of the ocean, the wind will be blowing one way and there will be a gentle current in a different direction. So it's very, you don't want to foul your propeller. Then you're really in trouble, right? So, but now they've got what they call Z drives, and so dynamic positioning is, and oh God, the captain would probably yell at me because I'm not really clear on this. But basically, you've got bow thrusters and you've got a drive that can go from being, when the ship goes, the propeller goes this way and you go that way, and they can turn them down and do this to hold you in place. So dynamic positioning means we can put something over the side. We say we want to be here, we want the core to go in here, and that's where the core is. And you're not drifting off, right, off your station. So those two things, so there's dynamic positioning, GPS, so we know where we are and we can stay where we want to be, and multi-beam. So I showed you that, the multi-beam, where you can actually map the bottom of the ocean. You can actually get a, so what it does is it sends out a beam that's an arc. And so you can see a stripe of the ocean. As you mow over it, you get a pattern of the ocean. Single beam echolocation gives you a point. And so, you know, there's a way to read, you can read it, but when you go through a canyon with single beam, you get side echoes, and so you get all of this, you lose a lot of information, but multi-beam gives you those beautiful, I showed you those beautiful canyons, and so that's the other thing, the multi-beam where we can see the bottom of the ocean. It's like, before that, it was like, and I'm older than multi-beam, it was like going around with, like, you know, with one eye patch on and like a magnifying glass, and you okay, that looks pretty good, and now I got my glasses on, I can see everything. So those are the technologies. So just being able to see what you're doing, seeing where you are, I'm not going to predict. How's that? But yeah, it's really made a big difference. Yeah. Am I going long? Oh, online. Yeah. I'll come back.
Is a diatom like a foram? What is the difference?
A diatom is a phytoplankton. So it actually photosynthesizes, and it also makes a siliceous shell. A foram is a zooplankton, so it has to eat for a living. Some of them actually farm diatoms in their spines, and so they actually are carnivorous. And so they make a calcium carbonate shell. It's a good question, because diatoms are basically the most famous thing that anyone would know. If you didn't know anything, any other organism in the ocean, you'd know a diatom. But they're much harder to work with too, because they're smaller. You can't sort them, and they have spines that they stick to each other. So, but yeah. But thanks for the question. I saw someone over here. Yeah.
How do you ensure reliability of the course you build? Like, do you do like consistency checks across course, or? Say
again, louder.
How do you ensure reliability of the course you build? So do you do like consistency checks across course?
Well, if we're trying to correlate between cores, that's very, very important. So we have, that's what stratigraphy is. So we have radiocarbon dating, we can do Delo 18 wiggle matching between cores. So if we're trying to do a multi-core study, like a lot of the stuff I do, we're trying to look at different depths in the ocean. So yeah, so we basically do a lot of, you don't really do quality checks across them, but when you go from being depth in core to time, that's when we have to think about being consistent. So yeah, we do a lot of that. We do a lot of correlation between the cores to make sure we're in the same place in time. Because like I said, if you don't know what time it is, it doesn't matter what the temperature or the CO2 was. It's just sitting there with no place to be. That's a really good question. That's probably, again, that's one of the most important things we do. Not the science, getting the time right, getting the stratigraphy right. It's really important. Yeah?
Along the Atlantic continental slope, you have areas of sloping, mass wasting, turbidity currents and stuff. Do you have to avoid those areas?
Oh, absolutely. Yeah. Yeah, so I showed a picture of this. Yeah, that was that, you know that track where you hear for the beginning? That was like, no, slump, 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 scouring. You can tell that from that sub-bottom penetration. You can tell from looking at that whether the sediments are any good. And we were very hopeful off of New Jersey. I think we got one good core. But off of Nova Scotia with those really great canyons, perfect. We just avoided the canyons and it was like magic. But off of New Jersey, and can I get that? Can I get out of
Yeah, try hitting escape.
again? Okay. I can just, it's too far back actually, that's the problem. But let's see if we can get now you get to see the whole talk in reverse. But I would really like to show that because these are really good questions. This is the art, if you will, as opposed to the science of what we're doing. The art is in here. So that's a pretty good location. That's a slump. So I'm not showing you the whole trace. We mowed down the hill and we thought, oh, that looks good. But what we're seeing here, I can reach better here. So what we're seeing here, this is a pile of sediment that fell off of that slope. And if I go back a little bit more, that's Nova Scotia. But here, I didn't zoom in on this. But see, there's no canyons here, right? And so there's these little teeny things. This is Hudson Canyon, very famous deepwater canyon. But all these little chutes turned out to be exactly that, chutes. And mud's coming down there and just... I have miles and miles of data I could show you of where not to core. It's a good question. Yeah, no, it's like, yeah, that's my hardest job.
Yeah, when you drop your pipe into the mud and you bring it back up, what holds the mud in place in the pipe?
That's that core catcher. So it's like we take a sheet of metal, we cut holes in it so it's got fingers, and then you bend them so that they're like this. And so that's actually sitting in the core, and the mud's pushing that back as it goes in, and then when you're done, it makes a fist. Now, if the mud's mud, you're good. If you're worried that the mud's sandy, we add a sock to that. I kid you not, we put a sock around that too so that it won't slump out. So some cores you could have nothing there and they'd come back just fine. Other cores, you know, depends on the mud.
One other thing, does your research ever show anything about evolution of plankton?
I work on too short of a time scale. My favorite phytoplankton in the Southern Ocean, I can give you an example. I work on 250,000 years is my limit because of what I'm interested in. And one of the more important phytoplankton in the Southern Ocean evolved from one species to another at about 180,000 years ago. And so that's right at the edge. So that's pretty recent for phytoplankton to change species. So no, I'm kind of what I do, no. But for other people, yes, that's really important. We have a whole, if you work on longer time scales, biostratigraphy is important. When did that foram it go extinct, and when did that foram or phytoplankton evolve? Gives you a nice time stamp when you're too far back to be working with radiocarbon or some of the other dating techniques. So it's actually quite important. So that's a good question, but not me.
I was just curious about the evolution of whales based on what they go after some of the plankton species. I was just curious how that might have changed over the millennium.
Well, yeah, no, the thing is, I don't think they're species specific. I think they're more sort of, whether it's, there's a couple of different species of Antarctic krill, which a lot of the whales like to eat. And I don't think they really care whether it's Euphausia superba or Euphausia antarctica, just as long as there's enough of them. It's kind of like, do you like rock shrimp? Or do you like North Carolina, what is that, mud shrimp? I'll eat shrimp, right? So I think it's more like that. I don't think that level really matters to them, as long as there's enough to eat, I think, is more the thing. But if you have what we're dealing with now on short time scales here in Antarctica is you're having changes in whether there are krill or whether there are salps, and that's a big deal, depending on the temperature. And that's not evolution, that's ecological. So that's more of a short time scale thing. But yeah, no, it's relevant. Not for me.
You were showing the dual beams.
Right.
And they were, I was wondering, because I was thinking about this like archaeology a little bit, but is that like...
Yeah, they have a ground penetrating radar. Yeah, it's similar thing. It's a similar technology, different wavelength, right? We use different wavelengths. Actually, that's a good question because for looking at how, so that multi-beam is 12 kilohertz. The sub-bottom penetrator is 3.5.
Oh, so you put them together to get that?
One gives me the surface, one gives me about 30 meters of penetration to see what's there. And so it's just a different frequency to get different effects, and it depends on your medium, right? We use radar for weather and that's a different frequency, right? Yeah, sorry, I'm looking at the weatherman over here and making sure I'm not making it, but it's just, these are all radio waves with different parameters that give us different information. But yeah, it's very similar. And if I want to look really deeply, I use a different frequency, but let's not go there. So, all right. One more question? Okay, one more question.
If the ocean does in fact absorb a lot of CO2 from the atmosphere, looking at ice ages versus non-ice ages, comparing atmospheric CO2 to ocean CO2, do you find the one's always the inverse of the other?
Yes. I would say qualified yes. So on the time scales of ice ages, so tens to hundreds of thousands of years, let me put it this way. The only exchangeable reservoir on the Earth that could impact the atmosphere that fast is the ocean. And what John didn't say this morning, what he said was absolutely correct, but what he didn't add is the deep ocean is like a soda bottle with a cap on it. So the surface of the ocean holds all the CO2 in. And so there's a lot of it accumulating in the bottom because there's a lot of organisms that die and fall down, and then they decay and they give off CO2. So there's way more CO2 in the deep ocean than in the surface. Long story short.
One goes up, the other goes down pretty much?
On 10,000 year time, 10,000 to 100,000 year time scales, yes. When you're talking about the millions and hundreds of millions of years that Sean was talking about, then you have to get other parts of the carbon cycle involved, and that's sediments. Yeah, other factors. So usually that's like fossil fuels and limestone, and those are the two other arms of the carbon cycle that, if we do a different topic next year, I can come back and talk about that. It's a whole different topic. But yes, on short time scales, it's ocean atmosphere.
So that would prove that it is absorbing that.
Yeah, I would say 90%. There is someone, if you were here earlier, it was also, sorry, this is getting complicated, but yes, terrestrial biosphere, so soils and trees and stuff, they're in there, but the ocean is basically the elephant in the room, okay? All right, thank you.